All right, everyone. So our next lab is on magnetic force on a current carrying wire. So this is going to be our first experiment in magnetic phenomena where the objects are being pushed or pulled due to the presence of a magnetic force or magnetic field rather than electric force and electric field. So there are some similarities and differences between electric and magnetic forces. But one thing we have here is let's look at sort of like, let's say, how we can generate this, what we call magnetic fields. For those, we need magnets. So let's say you have a magnet. Here's a piece of magnet. And I'm pretty sure everybody knows that magnets have two sides, right? There's a north pole, and there's a south pole. So let's say this is a north pole of one magnet. And then we'll bring another magnet and put it like this, and we're just looking at some small, the left end of this magnet, and this is going to be then the south pole. So this is the north pole, and that's the south pole. Then there's going to be an electric field from this configuration going from north to south, kind of similar to when you have two charges, positive, negative charges. There's an electric field between them. So let's say the magnetic force will be in this direction like this. And we have capital B representing the magnetic field. All right, so the magnetic field, kind of similar to electric field, right? They have magnitude, they have direction, and they need to have some kind of source, and the magnets are the source. If you think about then this configuration, this is kind of like a rough picture. So the idea is that we can assume, let's say, that magnetic field is uniform in this region. So technically there could be some edge effect. That means maybe here the magnetic field goes like this, but let's only concentrate more or less at the center part where the magnetic field goes more or less uniform and parallel to one another from the north to south. All right, so then this magnetic field, kind of similar to the electric field, will exert a force on a charge. But it's not quite the same, let's say conditions apply to the magnetic force as it did for the electric force. So for example, if I place a charge right here, so let's say some kind of positive test charge, what I will have here is if I place the positive test charge over there, well, there is no magnetic force. There is no magnetic force right now if I just place it there and let go. It will not be pushed or pulled. Simply because one of the key requirements for the magnetic force is that it has to be a moving charge. For the electric force, it doesn't matter. For example, if those blue lines were electric field and I place that charge over there, there's going to be a right away electric force acting on it. But magnetic force requires a velocity. That means this charge has to be moving. Now, also, let's say if this charge was moving in this direction, parallel to the magnetic field, there again will not be a magnetic force. Because one of the requirements here is this. Magnetic force on a charge, obviously, this particle being charged is another requirement. So it requires that particle to be charged. So it's proportional to that. So it's proportional to the particle to be charged. That means, greater the charge, stronger the force acting on it, but it depends on directly to the charge. It also depends on the magnetic field. Obviously, if there is no magnetic field, there will be no magnetic force regardless. So those are the two things, right? There's to be charged particle and there's to be magnetic field. But one thing it also depends here is if it's a moving particle or not. So velocity is an important component for the magnetic force. So we put like FB, magnetic force. But moving is not everything. In which direction and how is it moving relative to the magnetic field is a big factor as well. Because if this particle moving in the direction of the magnetic field or in the opposite direction of magnetic field, then it will not be subject to the magnetic force. There will be no force acting on it as long as it's moving along the same line as the magnetic field. Because this magnetic force also proportional to the sine of the angle theta that magnetic field and velocity make relative to one another. And you can see, right now, magnetic field in a positive x direction, velocity in a positive x direction, theta between them is 0 degrees, sine of 0 gives you 0, there is no force. That means there has to be at least some kind of angle theta that is between, let's say, 0 and 90 or something like that. So, for example, if this particle would happen to be moving like that with the velocity, in a y direction, compared where the magnetic field is in x direction, theta is 90 degree, then you do have, let's say, magnetic force. Even if, let's say, if it's moving maybe sort of like an angle like this, right? This is the velocity. Then you can say, right, with respect to this magnetic field that is right there, then you have this angle theta. And that's what, sine of theta basically takes care of. All right, that means what we have is magnetic force acting on a particle is equal to then QVB then sine of theta. Okay. And you can see, right, the conditions have to be right in order for there to be even a magnetic force. And even the direction of the magnetic force is not as straightforward as the direction of the electric field, electric force. Because electric force has either the same direction as electric field, if the test charge is positive, or the opposite direction of the electric field, if the test charge is negative. Magnetic force always perpendicular to both velocity and magnetic field as vectors. That means you can see, right, if the magnetic field is in a x direction, if the velocity in sort of like, let's say it's in a y direction or such that basically both of them is in the xy plane. Let's say here's a magnetic field, here's a velocity, right? And this angle between them, if both of them in xy plane, then magnetic force actually out of the page or into the page. So hopefully you guys are aware of that the right-hand rule can be used, right, to find then the magnetic force direction using the right-hand rule. In this particular case, right, if you use the right-hand rule, you should be able to see that force is basically into the page. Magnetic force for this is into the page. Right, your fingers in the direction of velocity, you curl your fingers using your right hand, right? You curl your fingers toward the magnetic field, and your thumb should be pointing into the page, which means that that's the direction of the magnetic force. All right, so that's kind of what we have for the magnetic force in terms of it requires a moving charge. So now what we're going to do here is, obviously our lab is not, magnetic force on a moving charge. It's on a current carrying wire. But here's the thing. What is a wire? Well, it's some kind of conductor. So let's say it's some kind of conductor like this that has a bunch of those wires, right? There's a bunch of those wires basically going from one end to other. Remember, if we talk about current, remember current is defined as flow of charges. That means what I have here is there's a moving charges inside the conductor that, that provides some kind of current. Okay, so remember, the definition of the current is the flow of charges, right? Delta Q, delta T. So remember, this current is delta Q over delta T. All right, now how can we then relate this equation that I just derived for the moving charge to the current? Well, think like this. Then what I have here is region where the part of the wire now is in this magnetic field, right? That means more or less from here to there, that means in this length L, any charge that's moving through the wire and goes through that length L, because that length L in this region where there's a magnetic field, then will be subjected to magnetic force. That means when it enters that region where there's a magnetic field, there's going to be a magnetic force. And even, this equation more or less can be used. So here's what we have. Force, magnetic force equals then QVB sine of theta. Now, V is the velocity of the, the particle, right? As it goes, let's call this from point 1 to point 2. As it goes from point 1 to point 2, it's moving with some velocity V. But remember, I can also represent velocity V in terms of distance over time. What is the distance it's going to cover? Well, it's a distance between 1 and 2, which is the length. And this will be then in terms of this, time interval delta T. Okay. Well, that's the velocity. which is L times delta T. So if I come back to this equation, I can say that magnetic force is equals to Q times, replace V with L times delta T, then magnetic field strength times the sine of theta. Well, from here, I can see that if I kind of rearrange that equation, so I can write this Q delta T L B sine of theta, and I can say, right, this Q delta T, or in a way, delta Q delta T, if I look at basically more charges that's going through here, right? Q delta T is nothing but the current. That means this represents any charge going from point one from point two to that magnetic field region will be pushed or pulled because of this magnetic field. So Q over delta T, or delta Q over delta T, is the current. So this becomes I L B sine of theta. That means this is then the equation of the magnetic force acting on that region of wire when the charges are moving. Think like this. You can see, right, if there is no current, there is no magnetic force. If there is no magnetic force, because the magnetic field, there is no there is no magnetic force. Also, how the wire, orientation of the wire. If the wire is in the same direction as, let's say, the magnetic field, again, there will be no magnetic force. That means what we have here is this. This is our equation. F of B is equals to current in amps, length in meters, magnetic field in Tesla, and then sine of theta. And that's the equation that we're going to be using for today's lab. This equation tells us that if you have a current carrying wire, then if you measure the length of wire that is basically in a region where there is a magnetic field, force is directly proportional to the length. Well, force is also directly proportional to the current. Also, force is directly proportional to the angle, it does proportional to angle theta, but in terms of magnetic field. Now, our experiment will take theta to be 90 degrees always. That means sine of 90 basically becomes just 1. So what we're going to look at is this. Magnetic force equals I times L times B. So we have this equation where it says force is proportional to the current value, length value, and the magnetic field. And all of those are direct proportionalities. And that's what we're going to explore in this lab. Is the force directly proportional to length? Is the force directly proportional to current? And is the force directly proportional to the magnetic field strength? And our experiment should allow us to verify that. All right, so let's go ahead and look at our experiment, where we again going to be verifying those things using basically this theory for the magnetic force on a current carrying wire. All right, so here's the experiment. So you can see the learning objectives is to explore the factors that affect the amount of force on a current carrying conductor in a magnetic field. So here I give you some theory, background, right? And then let's go to the apparatus. So this one is a relatively straightforward apparatus where we have, you can see, right? So it kind of like, tells you step by step what it is. So let's say this is our magnet. All right, so this is our magnet over there. And you can see, right, so this is the wire. So this is the wire. Okay. So the magnet, we have the wire. And this magnet basically generates, you can see, right, those blue lines. Those are the magnetic fields. That means the red arrow represents in which direction the current is going. That means those charges are moving from right to left. But there's a magnetic field into the page. That basically means it's a magnetic field into the page. Now, which means as this charge is moving from right to left, that means that the right represents the direction of the current. Into the page, there is a magnetic field, which means that they are perpendicular, right? So that, the current, length of the wire, and magnetic field, right, they're perpendicular to one another. Right. So as soon as we turn on the power source and there's a current running through the wire, magnetic field gonna exert force on those wires. And that force strength, right, can be then measured using using this scale. So the scale measures force on the conductor. Well, scale measures the mass, not necessarily the force, but we can then, convert, right? Remember, force. So it basically represents in terms of, like, let's say this pull, like, let's say downward force, which is equal to the gravitational force. So we can say this is just equals to mg. So mass in kilograms, right? Times 9.8 meter per second squared, then can give me the force. I give you like a sample equation that allows you to calculate that. But this is pretty much the apparatus itself. So once we have a current running from innovating like this, so this is going to be our 0.1. So here is going to be 0.1, and then here's going to be 0.2. Why? Because this wire is, there's no magnetic field over there, so we can kind of ignore that. Only this portion, right, from 1 to 2 is subject to the magnetic force because there's a magnetic field in that region. So that means that's basically the length of our wire. And one thing we can do here, we're able to actually, change the length of the wire. We should be able to change the magnet itself, right, in our experiment, and also see how the magnetic force will be then related to some of those quantities. Okay, so let's go and see what we have. There we go. So this is few sort of like, let's say, initial questions. You should be able to, like, let's say, answer it using the right hand rule, let's say ID and things like that. So basically be able to, let's say, answer this couple of questions, and even here I give you how to calculate the force, because, for example, one thing you can see here is when there is some certain force acting on it, let's say certain current going through the wire, you can see, right, you are given in terms of the mass. Let's actually play that. There we go. That means you can see, right, as soon as you connect, see, there's a right away magnetic force, and the magnetic force pushes it down, and the scale basically is able to measure it. So going back to the, playing the video, we can see that, let's say starting from when it was 0, as soon as we make a connection, so it goes and shows that there's a force. So this one allows us to measure. Let's see what we get. So from here we can see, that's what I see. All right, so when make a connection, let's pause. It does the same thing again. Okay, I'm gonna pause. I'm gonna, then look at it in terms of what we have. So we were here, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So assuming that they're increments of grams, right? So 100 and maybe 4, 100 and maybe like 6. It would have been much easier if it actually went to the other side. But so this is kind of what we get. So this is counting, like, let's say I went from here to there. It will allow you to measure the amount of mass. Okay. So let me see, let me clean this up. Okay. All right. So let's see. Why does it say 78 gram? I'm not sure. I did not measure 78 from here. Okay, but in any case, so you should be able to find it, and it's in grams, and then take the value in grams, convert it to kilograms, times 9.8, then you get the force. Okay, so that means you should be able to find the force by taking the mass in grams, convert it to kilograms, times 9.8, and that's the strength of the force. All right, so then we have 3 experiments. Part 2 is basically our first experiment, force versus current. Part 3, force versus conductor length. Part 4, force versus magnetic field strength. That means we are looking at exactly same, equation where we said the force is equals to ILB. So current, length, and a magnetic field. That means we're going to see how the force related to those quantities. And hopefully, when we do the experiment and when we do the graphs, there should be a direct proportional relationship. All right, so let's look at in terms of the first one, part 2, force versus current. Okay. So our goal is to discover how each factor that we change on the apparatus affects the amount of force on the conductor. All right, so obviously, as I said, right, it's the current. That means as the current changes, force should change. As the length changes, force should change. As the magnetic field strength changes, force should change. So we are given 4 different types of magnets, A, B, C, D. So they're given as A, B, C, D, and you're given their values. I'm going to use A to show you sort of like some sample, measurements. So you then use B, C, and D. So do not use magnet A for any of your measurements. So I'm going to use that for the sample, measurements here. All right. So the first one is going to be finding how the force related to the current. Okay. So this is our apparatus. So the idea here is this. So once we turn on the power source and increase the voltage in a power supply, so there is a ammeter that measures the current. Okay. So then the current will go through those wires, and then at this region where there's a magnetic field, there's going to be force acting on it, and then the scale is going to measure the force for each specific current. When we increase the current, right, there's going to be a specific force. And that's what we're going to be measuring. So let's watch the video. You can see how as we increase voltage, the current increases, and then the force starts increasing. Then the force scale shows increase in the force value. Our experiment going to be measurements of current, which I give you. So you're going to measure how the mass and force changes when the current changes by increments of 0.25. So I have 0, 0.25, 2.5, sorry, 2.5, not 0.25, 2.5, 5, 7.5, 10, 12.5, 15. Because if you look at the video again, right, the current goes from 0 to roughly about 15 amps. There we go. So we can just go all the way about 15 to make a measurement. That means what you do here is you look at your 0 as a first measurement. So you can say, okay, so when the current is 0, what is the reading? So you can zoom in, you can see, right, that's basically 0. So you come back and say mass is 0. And then force, well, force is a measurement that requires you to take the mass, convert it to kilograms times 9.8. So you can say, change the column formula, take the mass, convert it to kilogram. Remember, it's going to be in grams. To convert to kilogram, you just need to divide this by 1,000, and then times 9.8. And that will give you the force. Okay. So then you look at in terms of what you have as a reading for mass when the current here is 2.5. So let's say you go and see what happens. You can see, right, those marks on the ammeter, those are increments of 0.5. I think 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, then you get 5. That means each mark is half an amp. So then we go and find 2.5. Which is right here. Right? So that's 2.5. So this is 1. This is 2, and this is 3, right? This is 4, and that's exactly 2.5. So then for 2.5, then we go back. Then we go back and see what's the reading on the scale is. Well, this is increments of 2. Each mark here is 2 grams. So we have 2, 4, 6, almost 6. So I can say maybe 5.8 grams. So I can come back here and say, this is 5.8 grams. And then you can see right away, you get then the force because you're calculating. Then we go into 5. So 5 is a little bit easier to get. So right there on the line. And we go and look at the reading. So this one increased to about 2, 4, 6, maybe like about 6.8 or something like that. Because remember, it goes increments of 2 grams. So it's a little after third mark, which third mark is 6. So maybe about 6.8 or something like that. So you come back here and say, all right, 6.8. Enter, and you get the force. I'll do one more, and then it should be enough in terms of for you guys to get, let's say, the pattern. All right, so I go then. So this is 1, this is 2.5. Then I look at the reading. I get 10, a little bit more than 10. So I would say this is 11. So 11 grams. So I come back here and say, all right, it's 11 grams. And enter, and then I have the force. All right, so let's then go and see what we can do for this. I already have enough data that I can, basically be able to see the pattern and the shape of the graph. So I go and plot force versus current and see, like, let's see what I get. Now, is this proportional or not? So I pressed, let's say, and I can see that, well, this is a little bit off, but remember, you need to have 3 more data points, right? If I did, then the graph probably would have been more or less. So it's not ideal because this, especially the mass scale value is not very accurate. So, but the idea here is you can see, right, it's increasing, the force is increasing as the current is increasing. Is more or less, linear relationship, proportional relationship. So that's what you have to do then for your configuration. So what you're going to do here is when you are doing the experiment, you're going to go and choose different magnet. You can choose different magnet or different conductor, doesn't matter, as long as, anything other than what I used. You can say A and 2 or B and 3 or something like that, right? So then what I have here is, this is where it says pound, right? Change that with your configuration I give you, right? So if you have magnet B and number conductor 2, change that to B2. So then I can see that which data, which conductor, let's say you're using, right? So mass, whatever for the magnet and conductor configuration you're using. In this experiment, the idea thing like this is this. Force is equals to I, L, B. B, we keep it constant. L, we keep it constant. And we just vary current and see how the force changes. That's the idea for this particular part of the experiment. All right, so next, there's a question that you get to answer once you do the experimental, take data, do the graph, then you should be able to answer this based on that. The next one is force versus conductor length. Okay, so in this case, what we have is this, right? Again, same thing, force is equals to I, L, B. Here we're keeping B constant, right? So we're going to choose a magnet and some number of conductors. Then we're going to vary the current and measure what's the force on a wire when you have this magnet and this number of conductors. Then for the second column, so you're going to do three measurements here. For the second one, you're going to keep the same magnet, right? Repeat this 2 more times with the same magnet, but different number of conductors. All right, so again, I have the data table that's already, I give you the sort of like, let's say the columns, what you should do. So you're going to measure the current, right? 0.0, 2.5, 5, 7, 4, 5, 10. So I give you about 5 measurements for this one. So you're going to go and say, okay, so I'm going to use A and 1 to demonstrate this. Then you use something other than that. But once you choose one magnet, you're not going to be able to, that means, choose. So that's why you have 3 data. So magnet B, magnet C, and magnet D. So you're going to basically do all 3 of them. So let's say, one thing you're going to do, whatever I'm doing for for A, you're going to do them for B, C, and D. So here it goes. So A1, we start with that. Then exactly the same thing as I did above, I do this for A1. That means I vary the current and I measure the force. So for example, Again, for when it's 0, I can say it's 0, this is 0, and I can say then the force equation going to be taking mass divided by 1000, then times 9.8. Okay. So then I go and say, all right, so when it's 2.5, let's say roughly speaking, let's say this is 2.5, I get the current, sorry, I get the force. So it's about, like, let's say 6. So I think it's exactly the same data as I had above. So what did I have? 5.8, 6.8, 11. So let's do that. 5.8, 6.8, 11. Okay. So this is going to be my magnet, first magnet, right? Then you're going to do the same thing for magnet B, the mass, force, and magnet C. Sorry, you do magnet B, C, and D. So you don't use A, but you do B, C, and D. So you have 3 different ones. The idea here is this. If you come here and plot, let's say, this is your first one, not what, force, versus the current. Okay. So this is what you get. So this is what I got, let's say, for mine. Okay. Now I'm going to just make up data so that you guys at least more or less can see what I'm referring to. I'm going to make up data. The idea here is this, right? So we're going to increase the length. Okay, we're going to increase the length. And the way you increase the length is this. So you basically, kind of like doubling, right? So you're doubling the length, tripling the length. So when it says number of conductors, 1, 2, 3, so kind of like the wrap around one another. So then you have 2 or 3 or 4. The easiest way to actually see that the relationship in a graph like this would be this. So let's say once I go to conductor, for the same thing, right? Sorry guys, I want to make it clear what I don't know if I said it correctly a few minutes ago. You choose one magnet and you always use the same magnet. Okay. You choose, one magnet and always choose the same magnet. What you change is number of conductors. So this will be, let's say, what I'm doing here, I'm doing A1. This is then A1. The next, what I'm going to do, I'm going to be then A2. Then this will be then A2. That means same magnet, different conductors, number of conductors. So this is going to be then in terms of now, I go back and choose A2 and take the same data. That means what is the force for the same 0, 2.55, 7.510 current. All right, so play the video. And I can see, right, basically again, the force changes because of the current changes. And I go back and start making measurements. So again, when this is 0, this should be, let's see, if I go change the column formula, this will be A2 divided by 1000 times 9.8. All right. So then I go back and start making measurements. So I look at the ammeter when it's 2.5. Again, you try to do more accurately. That means you kind of zoom in and make sure it's 2.5. See, it's 2.5. And then you make a measurement of the mass. And I can see that this is basically maybe 4 point something. So maybe 4.3 or something like that. So I go back and say, all right, so 4.3. Then we go and look at the 5 amps. Right there. So then this is exactly 10. All right, exactly 10. Then I go to 12.5, 7.5. Right there. Look at the force or the mass. Well, it's almost 18, so maybe like 17.5 or something like that. So 17.5. All right. That means I have now magnet A, conductor 1, number of conductors 1, and number of conductors 2. And I do the same thing then for at least one more. I have like one more data for you, so at least one more, so 3 or 4, doesn't matter. The idea is that each one is basically a longer conductor. So then what do we see? Well, this is for the one conductor. Then here we go and add another column. Then this is going to be the force where I have 2 conductors, like this. And I'm going to get data like that. And I'm going to find, oh, this is the second one. So I get this. Again, it shows that there is a proportionality once you get the next data. So let me see if I do like a linear. Okay. All right, so there's a proportionality. Also, one thing I can see is this. For example, when I look at this, remember this is, let's say 2.5 current, right? Amps, 2.5 amps. I can see for this particular current, or any of the other current, maybe I have a feeling that this point that I measured is a little bit wrong. It's probably wrong. It's 5.8. Something like this. So if I go here, this was my 7.5 amp current. It tells me that this is force 7.5 amps when I have one conductor, and this is when I have 2 conductors, which is the length is increased. From what I can see is that for all of those values, right? Again, this is writing anomaly. So those values, as I increase the number of conductors, you can see, right, the force corresponding to that is now increased. Okay, is now increased. That means if I have more data, so this will be for, let's say, 1 conductor, that will be for 2 conductors, right? Again, higher force. Steeper the curve, higher the value of the force for that particular, let's say, measurement. And that's what you can use to identify if 1, is it linear graph or not? 2, is it increasing with increasing length of the conductor? Which, looking at those 2, you can see, right? This is 1 conductor, this is 2. For the same current, you have higher force. 1 conductor, 2, higher force, and so on and so forth. It means force will increase if you increase the number of conductors. All right, so this is how we verify force versus length, measurement. The last one is force versus magnetic strength. That means we are keeping, the length constant. In a previous one, part 3, we kept magnet constant, varied length. Here we're going to keep length constant, vary magnets. So we have 4 different magnets. Again, I'm going to use magnet A to show you demonstration, right? Sample measurement. And then you do B, C, and D. That means you have to do 3 measurements. And I already have a populated graph, a data table. So again, you're going to vary the current, then measure when you basically have B. But then what number of conductors you want to choose is up to you. But do not change that for other ones. That means if I go B3, for example, right? Then this will be B3. Just write it down. Then this has to be C3. And then this has to be then D3. All of them should be, for the 3rd, configuration, right? For the conductors. Yeah. That's the idea. But I'm gonna actually show you an experiment for A. So I'm gonna say for me, this is gonna be, let's say, I don't know, A2, for example. I'm gonna do A2. And it's gonna be then B2. Right, so let me do this. So I'm gonna use number of conductors 1. So A1, B1, okay. That means, I'm going to do A1 and B1. That means for the conductor number of configuration, right, is number of conductors 1. I'm going to then start with A and then go to B and then see, let's say, how those 2 change. That means as I go from A, which you can come back here, you can see, right, it's a weaker magnet than a B. B is, not double, but about 1.5 times stronger magnet. So we're going to see that what effect does it have on the force. Well, measurement is basically the same thing again. you increase that, and you increase current, you measure the force. So let's say if I come back here, so for 2.5, which is right there, so I'm measuring, well, it is about 5, so it is about 5. So I'm measuring here, so this was 0, this was now 5. Inverse the force again, you can say it's mass divided by 1000 times 9.8. So then if I go to the 5 amps, I look at the force, this is roughly, I would say maybe 7. Then go to, let's say, 12 and a half. Then look at the force. I would say this is about 11 and a half or something like that. All right, so let's say that's good enough. Then I go to magnet B for the same number of conductors and do the same thing here. That means I go 0, 0. So then this guy will be taking mass B divided by 1000 times 9.8. And I get that. So then what is the current, what is the force when current is 2.5? Right, so it's roughly, that's actually 6-ish, so maybe 6.5. And you get the force. Then go to 5 and measure it. So this is almost I would say like 13-ish, right? So almost 14. So let's put this as let's say 14, right? I'm just estimating a little bit more. So then 7.5. Well, this is almost 20, so I would say that's 19. Now let's say this is what I have. And the idea is then you're gonna again come back and say, here's my force A1, and here's my force B1. And I'm gonna plot this as a with respect to the current. And again, the idea here is this: each new magnet is stronger than the previous one. So then if you look at, you can do like proportional linear, right? So, and if you look at then graph 1 or plot 1 versus plot 2, so this one here is for the A. This the darker one is for B. And you can see again for every current, so let's say this is 5, right? 5 amps. Force for A, magnet A is here. Force for magnet B here is here, which means it's much stronger. Force 7.5. Here's the force for A, here's the force from B. And again, you can see, right, for the same current, you have much stronger magnetic force because you have a different, stronger magnetic, magnetic field, right, or magnet. And that again verifies that force directly proportional to the magnetic field. Stronger magnet gives you higher force for the same amount of current. All right, so again, from here, you just do the graph. On this one, you're gonna have 3. You can go and have a third one as well. So once you do the, let's say, remember, you can do any three configurations that I didn't use and plot it and see if it matches your expectation or not, and then just answer the question over here. All right, so that's about it for this lab.